All right, on this one, it says an office supply company sells X permanent markers per year for P dollars per marker. The price demand equation for these markers is P equals 10 minus 0.001x. What price should the company charge in order to maximize their revenue? What is the maximum revenue? Okay, so this is again the so-called price demand equation. It's supposed to help us determine what the price needs to be set. In order to get revenue from this price, what we always had to do was we took price times the number of units sold. So we use the R of X to stand for revenue here. It's equal to the price, P, times the number sold, X in general. So P, though, is equal to 10 minus 0.001x. We'll put that with the X. We're going to distribute the X into the parentheses. Rewrite R of X is equal to 10x minus 0.001x squared. So in order to find the maximization here, we're going to again rely upon our derivative. So we're going to find R prime of x, that's equal to 10 minus 0.002x. And we'll set that equal to 0 and solve. So as we've had to do so far, we'll solve for x here, subtract over the 10, divide by the number in front of x. Okie doke. So we're going to get a solution of x is equal to 5,000. Now that number is the number of units sold, in other words. So the actual revenue that they come out with for selling that number, R of 5,000, we can go back to our original revenue function, plug in the 5,000 for x, and see what we get. So here's what it would look like if we plug 5,000 into the original revenue function. I came out with a total of $25,000. The actual price they need to set that out according to the price demand equation, we'll plug in the number for x inside the P equals equation, which looks something like this here. I came out with $5. So the summary of all this is the maximum revenue is, in this instance, $25,000 for a price set at $5 each. This next example is going to take us a step further from the last one by incorporating costs, so we can also talk about profit. And so they give us the cost function here, and so we need to take and create the profit function from this information. Again, profit is created by taking revenue and subtracting the costs away from it. So for profit P of x, go back to the last example, you can see what revenue was. It's the same revenue function here, 10 minus 0.001x squared. Subtracted by this new cost function, they give us 5,000 plus 2x. Let's simplify that down a little bit. So P of x, we'll write it down here again. All the first terms, don't necessarily have to write those in parentheses, minus 5,000 minus 2x. So profit P of x, we'll write that as negative 0.001x squared plus 8x minus 5,000. And now this one would like us to maximize their profit and find out how many they would sell and how much should they charge now to maximize profit, not just revenue. So to maximize P of x, we'll take the derivative P prime. It's going to be equal to negative 0.002x plus 8. And let's set that equal to 0 and see what happens. Let's subtract over the 8, and we'll divide out by that number in front of x. Okay, and what we're going to get here is x is equal to 4,000. A slightly different result than we saw for revenue up above. So again, x stands for the number of units sold. They would need to sell this many units in order to maximize their revenue, or profit in this case. So the maximum profit here would be found by plugging this number 4,000 into the profit function up above. So you could see that profit function up there. And if we plug that in here, the profit would equal out to a total of $11,000. Now the price that they would need to set it at in order to receive that amount of profit and that number of units sold can be found by using the price function here, price demand equation. P equals negative 0.001, and we're going to multiply it by 4,000 from our X number above. That comes out with a total of 6 for $6. This includes some extra information from the last two examples we've looked at with the markers and trying to maximize revenue, profit, and so forth. But this one says, what if there's an additional tax added, or maybe like a tariff or something like that? But there's an additional $2 added in to the cost for each marker. Taking this into account, how many markers would they need to manufacture to maximize their profit as a result? And how much should they charge, and how much profit would they make? Okay, in this case, we need to modify our costs, starting from the cost function we had from the last example. C of x equals 5,000 plus 2x. We're going to add an additional plus 2x for the additional $2 per marker that they're specified up here above. So our new cost function with the new costs added in would look like 5,000 plus 4x. Now everything else from here would follow a similar pattern to what we did last time. Profit, P of x, as a result would be the revenue function from the original example, 2 examples earlier from here, minus the cost function. So you can kind of see similar setup and calculation in the last example. I basically had to distribute the negative and simplified it down. So to save you the time of having me do that again, let me just go ahead and write it out. After simplifying it, we'll get negative 0.001 x squared plus 6x minus 5,000. That's our new profit function. Again, I didn't show the full process because, again, it's just almost identical to the last example, just with some different numbers. Okay, and then we'll go ahead and find the first derivative, p prime of x is equal to negative 0.002 x plus 6. We'll set that first derivative equal to 0 and solve. And I'll go ahead and save y'all the time of having to watch me solve it again because it's almost identical to the last one. In this case, though, we'll get x is equal to 3,000 after solving it. So that, as a result, would help us understand what the maximized profit would be. So what we can do now is we say the maximum profit. We can calculate that using P of 3,000, where this is our new profit function, the one that we see up above. If you plug in 3,000 for that one, it'll come out with a total of $9,000. And the price that they would need to set that at in order to create that situation, here we go back to the original P equals equation, but here we'll plug in 3,000, and I came out with a total of $7. So versus the last example where we had a smaller cost, they need to up their cost to try to maintain their profit as high as possible, but they're still not going to actually hit as high a profit as we saw in the last example. Okay, in this one it says when a management training company prices its seminar at $400 per person, they find that 1,000 people will attend the seminar. They estimate that for each $5 reduction in price, an additional 20 people will attend the seminar. So the question is, how should the company charge the seminar in order to maximize their revenue? And what is that maximum revenue? Okay, so in this case, let's choose a letter to stand in for something. I'm going to use the letter X. Letter X is going to stand in for the number of price reductions that they make. So we're going to count up the number of these $5 price reductions here. And so if we have that in mind, then the price per customer would go like this. The price per customer could be calculated by taking the initial $400 price and then subtracting away 5x, depending on how many reductions they make. And the number of customers that would result from this situation here could be figured out by taking 1,000, the initial amount they expect to attend, and adding 20x, where they assume that 20 more people will be joining in if they reduce the price by another $5. X again being the number of price reductions. So if they do one price reduction, then they expect to get 1 times 20. If they do 2 price reductions, then 2 times 20 or 40 more would attend. And at the same time, they would be taking away $5 more each time from the initial $400 starting cost. So this helps us design our revenue function here. The revenue, we can create the revenue by taking the price per customer and multiplying that times the number of customers or attendees to this particular event. And so R of X will be equal to the price per customer, which we wrote up above as 400 minus 5x times 1,000 plus 20x. Okay, so we've come up with everything we need to get started at least. What I did here was I FOILed out this particular R of X function, and I came out with negative 100x squared plus 3,000x plus 400,000. And since we want to maximize the revenue here, we're going to find the first derivative, r prime of x. And r prime of x would be equal to negative 200x plus 3,000. And we'll set that equal to 0 and solve from there. So again, subtract the 3,000 over and then divide out by the number in front of x. If we divide out by negative 200 from each side here, we'll get a solution for x as x is equal to 15. So that now helps us know how they need to maximize the revenue. That's again, x is the number of price reductions they need to make by doing the $5 each time they do a price reduction. So 15 $5 price reductions here is kind of the idea in order to maximize their revenue. So their max revenue here, if we want to calculate their maximum revenue, we would plug this into the function r, the 15. So if I plug that into the original r function, negative 100 times 15 squared plus 3,000 times 15 plus 400,000, I came out with a number for this of a total of 422,500. And that's their maximum revenue at a price that we can calculate by doing 400 minus 5 times 15, because they're taking $5 off, but they're doing 15 reductions in price. That comes out to a price of $325. On this example, we're going to be looking at another optimization situation, but the issue is a little bit different here. This is another sort of dimensions creation thing where we're trying to measure things out and optimize things. Here it has to deal with trying to create a box out of cardboard, and we want the box to be 8 by 12 inches. In order to make the box, we're going to take this square piece of cardboard or rectangular piece of cardboard and cut out squares from each corner and then fold up the sides to make the rectangular box. And so the situation here is to what squares should we cut out from each corner in order to maximize the volume? Okay, so we're going to definitely need some form of picture to go along with this one to get a sense of how things are being built. So imagine having this rectangular piece of cardboard. Again, it's 8 by 12, and that's the dimensions here. We were going to cut out these corners, and they're square corners, so that we can fold it up and create a rectangular box from this. So let's kind of imagine that these are our corners we're cutting out here. They're all going to be technically the same size. My picture just probably doesn't show it perfectly. But the letter we're going to use here to represent the quantities is the letter X. X is going to stand for the length of the sides of the squares that we're cutting out. Okay, and now let's consider what's happening to this other sides after we take these and we subtract them and cut them out. From the 8, we're taking away 2, so 2x. From the 12, we're taking away 2, so we'll write it as 2x. We take 2x from each side as we cut out 2 squares from each side, basically, or the corners, and we take away the x's from each. So let's imagine our dimensions here in the 3 dimensions we have with length and height once we folded it up to make a box. And so the question I have is, what is this h represented by in our different letters? In this case, since we've cut out the squares and we fold it up, x is going to turn into the height along that side. So here's how we're going to be able to represent everything. Our width, we're going to write that as 8 minus 2x. Our length, we're going to write that as 12 minus 2x from our picture up above. And the height, h, of our box is given by the letter x. That helps us out because we'd like to maximize volume here. Volume of a rectangular box like this one is length times width times height. And so when we plug in everything here, L, we write down 12 minus 2x, W, 8 minus 2x, and H, we'll just put x. We're going to need to distribute and reorganize this thing. So what I did was I FOILed out these things next to each other in parentheses. That turns into 96 minus 40x plus 4x squared. But we still have that x next to it here on the side. So I'm going to distribute that x into the parentheses here. Let me go ahead and rewrite it something like 96x minus 40x squared plus 4x raised to the third. So that's going to be representing our volume here. Now, before we go any further, there is some consideration we need to make for how big these dimensions can be, the length, the width, and the height. So the 12 minus 2x is the length. We know length needs to be at least bigger than or equal to 0. Same with width, greater than or equal to 0. So the length being 12 minus 2x, we're going to put that greater than or equal to 0. And the 8 minus 2x, we're going to also put that greater than or equal to 0. And if you solve these two things here, for instance, on this one, you could subtract over the 12, write it as negative 2x greater than or equal to negative 12, divide out the negative 2, and that would actually make it look like x is less than or equal to 6, because we have to flip the inequality when we divide by a negative. Similar on this other one here, we have negative 2 greater than or equal to negative 8, divide out the negative 2, and we'll have x is less than or equal to 4. Now, what this basically means for us is, at most, x can be 4 or less than that. So, as a result, let's go ahead and find the critical numbers and see what that helps us say here. We take the derivative for volume. So if you go back up to where we were talking about volume up here, and take the derivative v prime, that's going to look like 96 minus 80x plus 12x squared. Now if we set that equal to 0 here, and we solve, well, we basically now have a quadratic equation that we need to solve. Interesting, but it's what we can do here. Now there is a GCF across all numbers. There's a GCF of 4. We could factor out the 4 and write it as 3x squared minus 20x plus 24 equal to 0. Now, frustratingly here, this is actually not factorable. If you try to go through and factor it, it's just not going to work. So our only option is to take our numbers for A, B, and C and plug them in like we're solving using the quadratic formula. The 4 in front has no meaning at this point, just the numbers left over in the parentheses. We'll call those A, B, and C. So if I plug this into the quadratic formula, it's going to look like negative 20 plus or minus the square root of negative 20 squared minus 4 times 3 times 24 all over 2 times 3. Simplifying that would make it look like 20 plus or minus the square root of 112 all over 6. Now we need to calculate that and see what in the world this is. It's going to be a decimal of some form. Here's what I came out with when I plugged it in the calculator. I did it with both positive and negative, plus or minus, and I came out with two numbers. X could be approximately like 5.1, or X could be approximately 1.6. Now, we're actually not going to be able to use the 5.1, but only the 1.6. And the reason why is up above, I mentioned that the X has to be less than or equal to 4. So it can't be greater than 4 for this to work. So that's going to tell us what we need to have here for the dimensions. The X is equal to 1.6, so the dimensions of the squares that we take out need to be 1.6 inches by 1.6 inches. That'll give us the biggest volume we can possibly have when we fold up the sides and make a box.